Alright, so today we're just going to do a quick review on electric power. So we'll start off going back to magnets and magnetism, since that's kind of sort of the starting point that leads into electricity. So important things to note when we're talking about magnets is magnetic field lines, always from north and into south, so out of the North Pole into the South Pole. The distance between lines indicates the strength of the field. So uniform field, all the lines are the same distance apart. If it's not uniform, the lines are spreading apart, and the closer they are, the stronger it will be. And also super important is the lines must never cross. On a number of the last couple of years of papers, they've asked for you to draw the field lines for on a single bar magnet or multiple bar magnets. So should be a really simple 1 or 2 marks for you to get if you can just draw them into the north, into the south out of the north, get that curved field line around it. What's important to note is that they do specify how many lines to draw. Draw 4 lines, draw 5 lines. If that's what they're asking, that's what you need to do. So make sure you just take note of that. And of course, vector addition. So that means if we've got, a one magnet and one magnet, we've got a south here, we've got a north here, then vector addition says that the magnetic field at this point would be in that direction there. Okay, so remember vector addition, we're always doing head to tail for our arrows as we draw them in. Okay, next thing that we looked at was a current carrying wire. So the field lines around our wire, if we had a current flowing there, then our field lines would be in concentric, just get down here, concentric circles around it. Using the right hand grip rule, thumb pointing in the direction of the current, the magnetic field lines in the direction that your fingers would go. So they'd be at each of the points, any given point around the wire, we would have magnetic field flowing or being generated. If we're doing it, it's a bit harder to draw it like that, and more often we draw the wires going into the page or the wires going out of the page. Now I've said in and out on the wrong drawing, so that is out, that's it, going in. Okay, think of it like the point on an arrow or the feathers, easy way to remember which way it's going. Okay, right hand grip rule says thumb in the direction of the current. This is conventional current. Fingers will wrap around in the direction that the magnetic field goes. So reverse field direction if the wire is going the opposite way. Alright, solenoids. Basically, what is a solenoid? It's just made up of multiple coils of wire, current flowing through. And if we need to, we've got another right hand grip rule. So if we've got some solenoid with current flowing through it, let's make the current flow anti-clockwise from the top. So if you're looking down, it's flowing anti-clockwise. It says, right hand grip rule says fingers in the direction of the current, making your thumb point in the direction of the north. Okay, and then the field around that would be much like that of a bar magnet. So we would have field inside, we would have a uniform field. Right, forces on wires. This is the sort of the foundational part for all of your motors work. So if we understand the principle or the interaction of the magnetic field on a wire interacting with a magnetic field, then we can extend that to what happens when we put that wire into a coil shape and inside a magnetic field. So first thing, the equation was F equals BIL sine theta if it's on an angle to the field, in which case we're only using the component of F that's perpendicular. And then we have another right hand rule. So this time the right hand palm rule, or the way I remember it is the FBI rule. And that's basically where you create your gun. So middle finger points out, that's F. Your pointing finger straight, that will be B, and then your thumb pointing up, and that is in the direction of I. So if we know two of the three things, you can work out which direction the other one would happen. Typically we know B, we know I, and therefore we want to know F. Sometimes we know F and B and we want to work out the direction of I. Okay, and similar to this is force on a charge, or on a particle, charged particle that's moving through a magnetic field. In this case we've got F equals B Q V, and it operates on much the same principle as if a current is in a wire, except this time it's now free to move inside that field. So for example, if we draw a magnetic field here, F is still use the right hand rule, the FBI rule. You've got F, you've got B. This time V is in place of I. The direction the charge is travelling is in place of the I. So if we have some positive charge coming in here, where are we going? We've got F into the page. No, we don't. We've got B into the page. What direction is the force going to be? You've got two people pointing up, three people up. I think the consensus is up, which I would agree with. So we're going to get this sort of circular motion happening, causing it to go up. If, however, we send a particle in that's negative, the process is the same, except it's going to send the charge the opposite direction. And if I, as I've done in this case, made it too negative, twice as much, then the force is going to be twice as much. So we're going to turn a much tighter circle or curve through the field. Okay, so if we've got our heads around those concepts, then that leads us into motors. Two key features that you need for a motor. So you need magnetic field and you need a current carrying coil. Now we don't have a motor if we don't have either of those things. Now obviously if those are the only two things we have, the motor's not going to work very well. So there are a number of things that we can add to help with the efficiency or to make it work better. Common exam questions are giving you a very basic motor from some imaginary student doing some imaginary experiment to then ask you, how would you increase the efficiency of the motor that is given? So you generally have a large list of things to pick from. They may ask you to select 3 things, or they may ask you to explain why a particular addition would make it more efficient. So increasing the size of your magnetic field. Why? Think of F equals Bill. Increasing any of these, increase B or increase I, or increase the length of the coil that's in there, then in any of those situations you're increasing the size of the force. So anything that will increase the size of the force means it's going to turn stronger, therefore making your motor more efficient or work better. Or if we think about F equals N Bill, as we talked about with motors, obviously more coils. So for every coil you're adding on there, you're increasing the amount of force, therefore you're increasing the how well it turns for your given constraints. Soft iron core for the coil, or a laminated soft iron core. We talked about the lamination stopping the eddy currents generating in there, which makes it more efficient. Why? Because it's going to strengthen B through the coil. Curved magnets, because the coil is then perpendicular to B for longer. And then finally, because we've looked at DC motors, the split ring commutator. This is what's required if you want to keep the motor turning. Without this, the motor does half a turn at maximum and then stops. So split ring commutator, why do we want that? Reverse I every half turn. Keep F in same So you want to reverse the current every half turn. what that does is keeps, for each side of your motor, keeps the force acting in the same direction, and therefore you've got torque acting in the same direction all the time, which keeps your motor rotating. Common to see a question about why adding a split ring commutator works, or what feature and why needs to be added to this motor to make it work, or it was AC, we want to convert it to DC, how would we do that, why would we do that, or what would the effect of the split ring commutator do. Something to that effect. Usually 2 or 3 marks available for being able to explain reversing the I every half turn to keep force acting on the same side of the motor, to keep it rotating. Inducing a current. So we looked at this in terms of, well, the prac we did, we had bar magnets that we ran down into a solenoid coil. We're having a look at the effect of different size magnets, the effect of how fast it went in, as to what that did to our induced current. So what were the things that we need? In order to induce a current, we had to be cutting flux. What does it mean to be cutting flux? It means there must be a change in the amount of flux in the coil. So we had EMF was equal to B, V, L. Depended on the amount of, or the speed that it was moving in, the size of the magnet, and how much of the magnet was going in, how big the magnet was in order of, or how many lines of coil we were cutting. So how would we increase the amount of current that we induced? We can increase the size of the magnet that we're using to cut it. We can increase velocity. We can increase the number of turns. Every turn that you start to add on means another coil that's cutting that flux. Okay, so we're just talking about flux when we've been talking about the induction of current. Alright, 3 interruptions over. So, flux, we'll try again. We have mentioned that in terms of inducing current, in terms of cutting flux, but just a quick reminder as to what flux is, or if we calculate it mathematically, it's AB, area of the coil. So A is the area of the coil, it's a C, and B is magnetic field strength, as we've done before. And important, maximum flux is, or occurs, when it is perpendicular to the magnetic field. So think about how many magnetic field lines you can fit in the coil. Most are going to happen when it's perpendicular, and most can fit through it. So for example, perpendicular, we would have something like this, that's where you're going to get maximum flux. If it's on an angle, then we want to use vector components. So we'd actually use flux equal to AB cos theta. Not often we see the components come up in the exams, but it can come in. Generally, it works out fairly nice. We're looking at this mostly in terms of generators, and so they're mostly concerned with either maximum flux or minimum flux. Next thing we were looking at was Faraday's law. Whoops. Where'd it go? There we go. Faraday's law, which is talking about the induced EMF. We've got the change in flux over the change in time, and then we multiply that by n, where n is the number of coils. I'm going to stick that out the front there. Just going to show you something here. If we break flux down, we've got EMF equals B times A. A is the area, so it's length times distance divided by time. Distance divided by time is what? Speed. Okay, so what that tells you is the faster that we rotate that, the greater the EMF we're going to get, which is something that we realise, but mathematically we can just sort of see that there. So, how do we change flux? What tools do we have available to us? This can occur by changing B, so changing the magnetic field. So you can either increase that or decrease that. So we can change B by a couple of different things. We could either move the magnet closer or further away, or we could vary it using an electromagnet. In terms of using or trying to generate current, it's not very effective, not the most efficient way to go about it. Although, if you've ever seen one of those torches which you can just charge up, they have a magnet inside, you shake it, it's got a coil there, you shake it, it will actually charge it up. That's effectively what we're somewhat doing there by moving the magnet, changing the strength of the field in that coil. We could change A, which means change the size of the coil. Again, not a very effective way to generate electricity. We could change direction of B. Easy enough if we've got an electromagnet, but again, not very effective if we're trying to generate electricity. So we can change the orientation of A. What's that mean? Change how A sits in the magnetic field. So rotate the coil. And that's where we're going to come across that in terms of generators. Lenz's law. This is how we determine the direction of the induced current. So the induced current creates a magnetic field opposing the change in flux. So you can kind of like, I suppose, use the FBI rule and then just reverse the direction that it would be if we're talking about a generator, or think about what magnetic field direction would oppose the change, and therefore what current would be needed for that magnetic field to be taking place. Okay, finally, generators. Effectively, we're going for the opposite of our motors. Here we're using kinetic energy to create electrical energy, as opposed to motors where we're running a current through there using the interaction of the current and the magnetic field to generate kinetic energy. We want to do the reverse. We want to use motion, use the rotation and the interaction with the magnetic field to create I. What we need to remember, critical areas are maximum flux, and this corresponds to minimum induced current and voltage. And when we say minimum, we're really meaning no induced voltage at that point, or no EMF. The other one is where we've got minimum flux. That's where we get maximum EMF, maximum current, because most field lines are being cut. Okay, so maximum flux, the coil's moving parallel to the field lines. At minimum flux, it's actually perpendicular, so that's where it's cutting all the field lines. That's where we're going to get the maximum change in flux, and therefore the maximum EMF. And thinking about that, to calculate max EMF that can be induced, you need to consider a quarter of a rotation. Okay, it's come up a couple of times in the past exams where they want you to look at the maximum induced EMF, or determine that for a generator given the size of the coil, given the magnetic field strength, given those things. So you need to look at it from its maximum EMF to zero EMF, which is 1/4 of a turn. From a generator, output. If we are connected to slip rings, then that means each terminal is connected to the same side of the coil all the time. That will produce AC. The reason that we want this is because it's easily transformed. We'll talk more about that in just a second. The other way that we could would be to use a split ring commutator, same as what was in the DC motor, and then the output would become this pulsed DC output, because the terminals would swap every half turn as they did with the motor. Transformers. More than meets the eye. Okay, basically what we've got for a transformer, two coils, one soft iron core, and importantly, a different number of turns for each of the coils. If they're the same, what you start with is what you will finish with. We need a different number so that we can either step the voltage up or step the voltage down. So if the primary coil, the number of turns in the primary coil is greater than the number in the secondary, then we will step down in voltage. If you have more coils in the secondary, then you will step up. Oh, or you could stop it. Let's try that again. Step up the voltage. Now, going to have to, pretty much a guarantee, you're going to have to do some calculations. So you've got NP on NS equals VP over VS equals IS on IP. So depending on whether you know the number of turns or the input and output voltages or the input and output currents as to which orientation of the equation that you want. But remember, number of primary equals number of voltage in terms of what's on top. Primary voltage goes on top, number of coils goes on top for the primary. Secondary gets inverted, so IS on IP, while the others are P on S. Okay, and we are assuming ideal transformers. So what we're putting in is what we're getting out. Question that would then come up is, how does it work? Explain how a transformer works. So what we need is we need a current flowing inside the primary coil. What this does is creates B. Super important is that it needs to be AC. This is to ensure a changing B. If it's a DC current, there's no variation in B. We're not going to get a change in flux to induce B. So then B induces a current in the secondary coil. And most effective when we've got that soft iron core. You're going to concentrate that magnetic field through the coil, maximize the induced current. Okay, some of the electricity equations or basic circuit equations will carry on over into this topic. I think the new things really are the things that may trip us up. We just need to be very careful. So power. Something that was introduced was RMS power. And so if we're using RMS versus the peak voltage, for example, so VRMS equals V peak voltage divided by root 2. IRMS equals peak current divided by root 2. And then the power, the RMS power, the root mean square power, is going to be VP on root 2 times IP on root 2, which is VP IP over 2. Important thing that comes up will be power loss in transmission. We've got power loss is caused by the resistance and the size of the current that's flowing through there. The current doesn't get used up. The voltage will get used up. So we've got power loss is I squared R. This is where transformers link in, and a common question relating to the explanation of the use of transformers to reduce power loss, sometimes asking you to justify an answer, so show through some calculations how this would help. So generally what we would do is we would want to increase V through a step-up transformer. What the result would be is that if V goes up, I goes down, therefore I squared R as a result has to go down, and therefore reduced power loss in transmission. I think that's it.